The first attribute that we'll talk about is called the attribute is called hidden layers, and these are the same for SuperCollider as well. So I have an @ sign in front of these, as in like for the max attributes, but the keyword arguments are exactly the same. So for the neural network, when we're creating the neural network, we can specify a number of hidden layers, and this is going to refer to the number of layers we have inside of the neural network here. We can also specify the number of nodes or neurons that are in each of those layers. So we'll pass in a list, and the number of elements in that list is going to be the number of layers that there are, and the integer that is the element in the list will be the number of neurons in that layer. So for example, here, there's one hidden layer, so we have one integer. That integer is a 4, because we have 4 nodes in that one hidden layer. If we said hidden layers 5, 8, 8, this would mean that we're going to have 3 hidden layers. The first one will have 5 nodes, and the second 2 will have 8 nodes each. Now you'll notice that we're not specifying the number of nodes in the input layer or the output layer. The neural network determines the number of nodes in each of those layers from the data sets that you tell it you're training it on. So if the input data set has, is XY values, for example, and is a bunch of data points that are 2 values each, it knows that the input layer will need to be 2 nodes. And if the output data set that you're training to predict into is a set of synthesis parameters that have 10 values each, it will know that the output layer needs to have 10 nodes. We could specify hidden layers 10, 5, in which case we'd have 2 hidden layers, one with 10 nodes, one with 5 nodes. You'll notice all of these examples here are fully connected. They are MLPs that are fully connected. And you'll notice that the way that the hidden layers are usually selected here is that I try to create a funnel shape from the input to the output. Here I have more nodes on the input layer than I do on the output layer, so my funnel gets progressively smaller until the output layer. Here I have more nodes on the output layer, so my funnel gets progressively bigger towards the output layer. And this is a good place to start when you're trying to decide how many, what should I put for hidden layers. Usually I start with one hidden layer, and I choose some number for the number of neurons that is in between the input and output layers, numbers of nodes. And then if the neural network isn't converging, or if I'm validating it and it's not being very successful at achieving what I want it to achieve, then I might try adding another layer, keeping that funnel shape, right? Or maybe for that one hidden layer, making more neurons and seeing how it does then. Start to build up some intuition about like what is a good starting place, which is what I'm telling you, like one hidden layer somewhere in the middle, and then sort of grow from there if you need to, is usually a pretty good strategy. Since we're looking at this structure of the neural network right here, I'm going to take a moment to talk a little bit about how the neural network actually does its prediction process, how it does the feed forward process. And this will bring us right into the next attribute that we'll need to look at. So the way that the neural network actually makes its predictions is it's basically one big math equation. And that math equation is mostly multiplication and addition. There's one more piece to it that we'll look at on the next slide. But the way that it does the math is it actually takes in its input values. In this case, we have 3 input nodes, so we'd give it 3 values. It takes each of these values and multiplies each of them by a different set of weights. So the weights are represented by these black lines. And so we would say if this input value is 0.1, we'd say 0.1 times this weight, and then send that value along to this neuron. 0.1 times this weight, send that value along to this neuron. 0.1 times this weight, etc. We do that for each input has a different set of weights, and then we send them along to the neurons in the next layer. Once all those values reach the neurons in the next layer, all those values are summed together. And additionally, there is a additional sum value, additional value that is added inside of this neuron, and that value is called the bias. And so this bias is owned by this neuron, and it is just one value that gets added to all of these together. Then there's one part I'm hopping over here that we'll get to in a moment, but then essentially we have a new value for this neuron, right? The sum plus the bias. We have a new value for this neuron, this neuron, this neuron. And then the same thing happens to go from this layer to the next layer. We take this value, we multiply it by a weight, pass it along. Take this value, multiply it by a weight, pass it along, etc. For all of the neurons in this layer going to the next layer, which in this case happens to be the output layer. And then once we get these values all sum together and we add the bias, that becomes the output value. Same with this one. We get these values all summed together, we add the bias, that becomes the output value. Now there's one piece I skipped over, which is that there is additionally part of the neural network called the activation. And the activation happens right here in the process, right after the bias is added. So we sum together all these values, add the bias, and then take that value and pass it through what's called the activation function. And the activation function is a little function here. We'll see bigger and more options for it, that this value gets passed through, and then after it gets passed through the activation function, then that value gets multiplied by the weights and sent along to the next layer. So that's right where that activation function happens. We're able to specify a different kind of activation function for the hidden layers, and we can do that with the attribute called activation. And we can separate and we can specify a different type of activation function for just the output layer, and we can do that using the attribute output activation. So we can control what kind of activation function we can put at these points in the neural network. Those functions are, these are the four different type of activation functions that we have available in FluCoMa. So we have the sigmoid function, and what the sigmoid function does is it can take in any value, negative infinity to infinity, and it will squash it down into the range between 0 and 1. And this is the sort of activation function or transfer function curve, if you will, of that process. And this is the equation. There's three others. One is the hypertangent function, which is similar, although it squashes the range to be between -1 and 1. There's also the ReLU function, which if the value is greater than 0, it will pass it through unchanged. If the value is less than 0, it will clamp it to 0. So any negative value going into the ReLU function will come out as 0. And then lastly, there's the identity function, which does nothing. It passes the value through just as is. Input equals output. There are some important things to notice with this. So let's imagine that we have this sigmoid function as our output activation. That means that the neural network will only be able to output values that are between 0 and 1. So if we're trying to predict if our data set has values that are up in the many thousands, like frequency values, for example, the neural network will always have a massive error. It will always be way off. It'll never actually be able to learn to predict a value up in the thousands because it will only ever output values between 0 and 1. So then when it checks that error, when it checks how wrong it is, it says, well, Ted wanted this value to be 15,000, but I'm outputting it as 1. That's a huge error, right? So it'll constantly, it won't be able to learn. It'll constantly have a massive error. If we have the identity function, we're only doing linear transformations because we're only doing multiplication and addition. That's the only math that's taking place in the neural network. And so what that really limits the kind of relationships that the neural network will be able to learn between the inputs and the outputs. These three other activation functions are all nonlinear transformations. These are clearly nonlinear transformations in that they have a warped or curved space to them. This one is also a nonlinear transformation because it is not f of x equals x. It is a nonlinear transformation in that it will distort the data in some way. In this case, it's a very sort of hardline distortion of the data. Just clamp anything below 0 to be 0. But what these nonlinear transformations do is they allow the neural network to learn nonlinear relationships between the input and output of what it's trying to predict. If we think about this as a metaphor as an audio mixer, we can start to see how these different things piece together, right? So we have these inputs, they're like, inputs to a mixer. These weights are like scalars, right? They're like controlling the amplitude, which is how we control loudness or amplitude in these creative coding environments. We usually do multiplication to control that, right? So we're scaling the different amount of inputs, and then we're summing them together, which of course, as we know, is how you just combine audio signals in these creative coding environments. So we just sum them together. And that's how we pass values from one layer to the next. We scale them like loudness, and we sum them together like we're summing signals. We do that for the whole feed forward process. And then eventually we get these output values that are like the outputs of the mixer, right? That are these values that are a combination of these different sub mixes that are created. And then we put them as the output to hear them. The activation function in this case works like a distortion function, which if you're familiar with distortion transfer functions, I mean, that's what they look like, right? We sort of often are in the most basic cases, like warping, distorting the extremities of the signal of the waveform. And so in this case, we're adding these like distortion functions in the middle of our audio mixer metaphor here of how the neural network is working. So, and then, the bias, as we add the bias here, sometimes people think about that as DC offset, right? We're just shifting the waveform up or down, offsetting the DC of the signal. That's, for some people, that's a useful metaphor. For other people, DC offset is like not a concept that is encountered very often. So activation, output activation. We can control what the activation functions are in our neural network here. Activation controls for all the hidden layers. Output activation controls for just the output layer. And it can be useful to have those be different sometimes. And we'll see some examples of that. There's a few more attributes to look at here. 5 more, in fact. Here are 4 of them. The first one is a very important one. It's called the learn rate. And what this does is it tells the neural network, once you make your guess and you compare your guess against the value that I actually want you to output, how far should you try to move in the direction towards the value I'm actually asking for? Should you try to leap there and try to correct as really strongly, or should you just take a small step there and maybe wait a little bit, do some more training and see what happens? And this can be a bit of a, some people want to turn the learning rate really high and just say like, well, let me just learn more quickly, right? Let me jump to the correct answer. But this can lead to some problems, which we'll see in a little bit with a visual demonstration, which is that the neural network, sometimes it'll hop over the right answer, or it'll get really distracted and go too far in some direction by some set of data, when actually most of the data wants it to go in a different direction. And so if we set the learning rate too high, the neural network can be led on wild goose chases and sort of jump all over the place. And if we set a smaller learning rate, it just proceeds a little bit more cautiously, a little bit more slowly, a little more cautiously. And that can actually be lead to a better convergence, lead to a better training, because we're sort of letting the neural network, look at the data a little more holistically, take its time, and really consider all of the data. Another attribute is called max iter. And what this does is it specifies the number of times that the neural network will use all of the training data before reporting out to us the error. So if I have 5 data points, like we did in the earlier example, and my max iter is set to 1,000, it'll use all 5 of those data points 1,000 times to train, and then it will report to me the error. You might see this term epoch used with a lot of neural networks and different types of training systems. Using all of the data once is called an epoch. So you could also say max iter is specifying the number of epochs to train before reporting the error. This attribute batch size, you can specify how many guesses it should make before checking itself against my desired outcomes and then doing its internal adjusting, its back propagation. So you could say batch size of 1 says every time you make a guess, adjust yourself. Or you could say batch size of 50, which would say make 50 guesses, keep track of how you're doing if you're getting them kind of right or wrong, but sort of keep track of that, but make 50 guesses. And then based on all of that error that you've just calculated, then adjust yourself. And what this can do is it can similarly sort of slow down the training process in that rather than making adjustments after every guess, it sort of tries to look at the data a little bit more holistically. Rather than going on wild goose chases every time it makes a guess, it says, well, let me look at 5, 10, 50 of these guesses and then determine where I should be making my adjustments, where I should be trying to point at in a better direction. And again, this is because sometimes we'll have we could have one piece of data in our data set that is out in left field. It's totally not similar to any of the other data points. And if we make a adjustment after that guess, we might try to go way off in that direction to try to get closer to that correct answer. But then the neural network will have to try to step back after that wild guess, right? On the other adjustments that it makes. And so batch size lets us take a little bit more holistic view and not be quite as excited. There's the attribute here called validation, which is a percentage represented as a decimal that the neural network will actually hold back and not train on, and then will do its own internal validation. Like I showed with my validation patch, it'll actually do its own internal validation automatically for you. And if it finds that validation is not improving, if it finds that the neural network is probably learned as well as it's going to learn, it will actually stop training. It'll actually back out of the training and then report to you the error. It's going to help you prevent what's called overfitting. Overfitting is when the neural network gets really good at making predictions for the data set that you've shown it. But once you bring it out into the wild and have it try to make predictions on data that it's never seen before, maybe because you have a new oboe player or the trombonist is now on stage during live performance rather than being in your data set, the neural network doesn't perform very well. And this is called overfitting because the neural network has fit very well to the training data. In fact, it is overfit to the training data. And so it's not able to generalize to more use cases. And overfitting is a pretty common problem with training neural networks. It's something to watch out for. And this validation can help prevent that. So using some validation either here or as I showed you in the patch, it can also be a way to prevent that. The last attribute that we're going to look at is called momentum. If we imagine this as a bird's eye view of a canyon, here's the bottom of the canyon. Here's the mesa over here. Here's another mesa over here. The goal that the neural network is trying to achieve is trying to burrow down into that canyon. It's trying to get to a minimum position. And if it's in that minimum position, that's a very low error, right? So this is the metaphor. Low error is a deep minimum position in the canyon. Where the neural network starts is going to be randomized. Like I said, it starts in a random position, so I could just move this to any random position. And these steps that it's taking, each one of them is a back propagation process where it is adjusting its internal parameters to try to get closer to that optimal solution. And so if we take the momentum all the way down for a second, maybe I'll turn this up a little bit. What we can see is that the way that it makes these steps is it always just checks where it is in the canyon and tries to go down. And wherever it is in the canyon, down is going to be perpendicular to these gradient lines, right? So if it's right here, it'll look around and say, where's down? Well, down is perpendicular to this line, so it's going to go that way. And it'll make some jump, go over here. This is the learning rate. How big of a jump should it make? This would be a low learning rate. This would be a high learning rate, right? Make a big jump or a small jump. And then it moves. And then it looks around and says, okay, where am I now? Well, down is this way, so I'll go that way. And it jumps over here, and it jumps over here, then jumps over here, etc. And you can see for something like this, it's going to hop back and forth across that canyon over and over and over as it tries to make itself work to the right. What momentum does is it will actually try to notice that it is generally going to the right, and then try to help itself continue going to the right once it notices that that's sort of the direction it is going in. This is kind of like momentum or inertia. It's the same sort of concept. So if I increase the momentum, as it starts going down, after these first few jumps, I mean, even after the second one, it starts to notice that, well, I tend to be going, I'll always aim down, but I'm also sort of going this way. So like even right here, look, this could go down. This would be down right here, right? If I was going perpendicular to these gradient lines, but because it has noticed that it's also going to the right, it tries to maintain that momentum of rightward motion and continue going to the right as well. And so this helps the neural network learn more quickly by taking a more holistic view of the direction it is going in and then trying to maintain that momentum. And this nice page here, you can check it out. Here's the URL. Also lets you adjust the learning rate here. Here it's called step size, but it's the same parameter. So I can adjust how big of a step should I take. And you can see that if the learning rate is too high, there's that problem of the neural network jumping all over the place, right? Adjusting too much, trying to get to that answer too quickly, and it starts to jump around and be chaotic. So that's undesirable behavior. The important thing about overfitting, and so the important thing here is to have the testing data and the training data be separate things that you're actually, separate data sets that you're actually using, right? So you don't want to train the neural network on one set of data and then test it on that data, because of course it will do very well. It'll learn from that data. You want to set aside some amount of data that you're not going to train it on, and then you're just going to test it on. And this sort of imitates a real world use case, right? If you set aside some data that it isn't trained on, that's sort of like the recordings or the situation where it will need to perform in the wild, in the real world, when the trombonist steps on stage in front of the microphone or whatever, right? And it'll have to perform there with that trombonist on those trombone sounds that it's never heard before.